Okay, okay, ma'am.
Good afternoon, all. Now I would be content to invite Dr. Rajesh Ranganathan, currently working as a professor at CIT Coimbatore. He heads the Advanced Integrated Manufacturing and Management Research Group AIMMRG at CIT, and he is the director for a Center of Excellence in Manufacturing Sciences, only center in India funded by Ministry of Human Resource and Development, Government of India. Dr. Rajesh obtained his doctoral degree in additive manufacturing from Loughborough University, England, UK. During his PhD, he was with the world's leading research group, Rapid Manufacturing Research Group. He holds various projects accounting close to 11.62 crores. Dr. Rajesh, for his outstanding work on diabetic food management, received a Young Scientist Award from Department of Science and Technology, Government of India. He is guiding researchers in different disciplines of manufacturing and management. He has well guided international PhD scholars, which were resulted in of couple. He holds 6 patents, 42 journal publications, and authored a book with Amazon US, holding its copyrights. He has guided 10 PhDs and guided and as well as guided 8 PhD scholars along with 2 research associates working in various research projects. The outcome of undergone research were a couple of new products in healthcare finding novel applications to its end user, providing benefit to society. He works close with diabetologists, orthopedicians, surgeons, dentists, and food product developing research institute. We welcome you to share your views on additive manufacturing for healthcare engineering, sir.
Hi, thanks very much for your kind introduction, and I would like to thank the organizers, madam, for giving me this opportunity to catch up with you. So today, the given topic, or the topic I'd like to discuss is on how we can apply additive manufacturing for healthcare engineering. And I would also like to share some of the live research case studies that we did from our research group in and around Coimbatore. Are you able to see the slide change?
No, sir.
Okay. Now, ma'am, are you able to see the slide change?
Yes, sir.
Okay. I think there is some issue when I go on full mode. So I'll just leave it as such and I'll go through it. In terms of research focus, we primarily take 2 major domains. One is the supply chain management, and the other one is the additive manufacturing, wherein it came down earlier. It was called rapid prototyping, then it was called as rapid manufacturing. Then following that, it was called as additive manufacturing or 3D printing on and off. So we combine these 2 major technologies, and combining these 2, we can explore into any number of products. But our focus is completely in the area of healthcare. So you could see some of the case studies that we did in terms of healthcare. So again, as I said, when we combine supply chain management and additive manufacturing, there are many individual domains within that area we can explore. But whereas from supply chain perspective, we only look into low cost, how we can manufacture products at low cost, how we can reduce inventory, how we can reduce lead time, and how we can bring about lean and agility from supply chain perspective. From additive manufacturing perspective, it is like how we can improve customization, how we can print complex profiled objects, how accurately we can print parts, and again, how we can reduce the manufacturing lead time. So these are the 4 major primary focuses from additive manufacturing side. And combining these 2, as I mentioned, it's going to be in the area of healthcare domain. To quickly give an idea about supply chain management, let's say that we order a product in Amazon and we get the product back to us. So by the time, or from the time that we ordered to the time that it comes back to us, there are n number of processes that is happening, or there is a bulk of chain of activities that happens one after the other. Upstream and both on the downstream till we get the products. So that entire set of activity is called a supply chain. We think we just pick the product from the online website, but it would have some wholesalers, some retailers, some manufacturers, some supplier, some distributors. So there is a big chain of activity which is happening. So that is a bit of an idea about supply chain. And speaking of additive manufacturing, like we all know about the subtractive manufacturing technology, wherein you tend to take a bulk of a product and you subtract what you don't want, and finally you tend to get a final end product. Whereas in additive manufacturing, we tend to put uh, whatever we want, or our imagination is a key in terms of additive manufacturing. If you are able to draw it, we can very well print it. So for drawing, we can use CAD as a drawing input parameter. So using CAD, we tend to draw an object, and from there, it need to be converted to the language which these additive manufacturing machines can understand. So that language is called a surface tessellation language. And from there, there is a pre-processing, a bit of fine tuning need to be done in order to print a part. So that is where pre-processing comes in. And once pre-processing is done, the parts can't print by itself. So we need to give some sort of supports. So the entire aspect of activities happen in terms of pre-processing, then the entire file is transferred and the building of the part takes place. So when it comes to building of the part, it tends to happen as one layer over the other layer, as you are pretty much aware of it. So then we tend to get the final part and we take it for post-processing, and we are done with this additive manufacturing. If we look at the inputs, like not necessarily it need to be a CAD design. We can take the input. One of the form is CAD model, 2D or 3D CAD model, and we can take the data from CMM, coordinate measuring machine. For currently they use much of this application for reverse engineering aspects. And when they thought of using CMM as a probe, then they thought, why not we use some sort of laser techniques? So that is where CMM laser came into picture. So you don't need to touch in order to obtain the cloud points. Even a laser beam is fine to do that. And within that, you have varieties of scanners which can scan a very wide range of products from a part maybe a size of 1 mm by 1 mm till a part of 100 meters. So it can be done through laser. And then comes an MRI scan, wherein any data under the skin can also be obtained. So that is where we use magnetic resonance imaging. So you tend to get the data from the MRI, and that also goes an input. And CT scan data is also used as an input. Primarily, if we are thinking of tissues, muscles, and nerves, then we think of an MRI data. And if we are just interested in terms of getting the data of the bones, then we tend to look into the CT scan data. So these are some of the possible inputs, and it is not limited within this. There is again yet another option, which is the hapticom, wherein you can touch and sense the drawing, and once you are done with that, you can use the data that you obtained or the part that you drew through hapticom can also be used as an input for the additive manufacturing. So mainly we use hapticoms when the profile is very complex, to which can't be done through any of the traditional CAD systems. So that is why we use the virtual prototyping application. So in general, so these are the possible input data types which can be given to an additive manufacturing system. And when we speak of additive manufacturing system, primarily there are two major types. One is the metals and the other one is the non-metals. So in our case, we tend to deal much with the non-metals or the plastics or the rubber-based items. So that is where the entire discussion of today's would be I won't be discussing anything from the metals perspective. It is mostly towards the non-metal perspective. And much of our research lies behind this polyjet printing technology. This was a polyjet machine which cost close to about 1 crore, and this we got in 2013. And from that time onwards, we were using. And when we got this, ours was the 7th machine in the world that we purchased from Stratasys. So we'll see how we have used this in our research perspective. Just to give a slight outline of how this polyjet works.
Phonics uses inkjet printing technology that can jet two materials at the same time. This allows you to produce models containing a whole range of material properties to more accurately represent your final product. Each layer of resin is just 16 microns thick. It can even mix two materials to create a whole selection of properties, such as this material, which is tough enough to simulate ABS-like engineering plastics in applications such as this, or even this, that can do this. With Object's 3D printing technology, you can take your design idea and rapidly transform it into a functioning prototype. And you can do this with all the subtle details of your intended product built in, including the different material properties of assembled goods, such as this part. Multi-material technology is that you can build up to 14 different material properties, textures, and shades into a single part in a single print job. Object has an incredible range of over 60 materials, from rubber to transparent to engineering plastics, with the ability to mix and match various combinations.
So we have seen a slight outline of what the potential of this particular machine is. So ideally, this is a typical or a classical example for this particular machine, wherein you can print a transparent part, you can print an ABS part, you can print a rubber-like part. So it is possible to do all these combinations in one single go. So that is one of the major advantage of this. When we go through the case studies, you'll be clear like where we used these different applications in our research perspective. So this particular machine uses primary material and a secondary material. So primary material is a dominant material. It can be either rigid one or a flexible one. In the previous case, if we see, like I can use the white one as a primary one and the black one as a secondary one. So combining these two, the white and the black, if I want to print a gray color one over here, over the sides, that I can do that. So that is called as a digital material. So this white one becomes a primary, and if I'm picking this black as a secondary, the combination of primary and secondary, I can make it as a digital one, and I can print a part in gray color. That is option one if I'm looking for changes in color. And option two is, let us say that I want to print a part which is quite flexible in nature. So I can change the level of combining the primary and the secondary material. I can change the show hardness value, or in a way I can say elasticity levels of these rubber pins. Either I can, if I put show D as 100, it will become a very hard object. If I put show D as 50, it will become as a bit of flexible one. And I can keep going down or keep going up in terms of improving the flexibility levels of this part. So that is why we use the combination of primary and secondary material. And these are some of the typical examples where you can print, or what you can print using this particular machine. You can print a transparent part, which was earlier possible only through a stereolithography system. You can print a very complex ABS-based part, which was only possible in selective laser sintering, and a different colored part, which was possible in 3D printing. And now, using this particular polyjet technology, you can print all these three different parts in one single machine. On top of it, we can also print a hard and soft material. That is, this is a rubber one, and this is a solid one. So in earlier techniques, we need to print this separate and print this separate, and then we need to bond it. Whereas in current polyjet machines, you can print these two combinations in one single go. So that was one of the major advantages. So having seen about supply chain, about additive manufacturing. We'll explore into the case studies. As I mentioned, healthcare is the domain which we focus, but whereas healthcare, it has n number of products and which is quite a very huge range. Within healthcare, we only focus on processes. And again, within processes, you have internal and external processes. And what internal is, anything that goes under the skin falls under the category of internal processes. And as you know, anything like these are some of the typical examples for internal processes, like plates and supportive devices, which is used in orthopedics. And external processes, anything that stays outside the skin falls into the category of external processes. And this is where our major research domain is. And this is where the area that we work on. We work only on the external processes side. So I'd like to take you through a couple of case studies. One is the clubfoot, in terms of what we did in terms of laparoscopic surgery in one and diabetic foot, dental aligners, and we also thought we'll give a try with peacock, how we did a prosthetics for a peacock. So starting with the clubfoot, we have seen, or we have came across people who had clubfoot, and this is one of the typical examples of a kid with a clubfoot. And usually children are born with clubfoot, and it was said that children who are born with clubfoot need to be treated within the first 3 months. They should start their treatment within first 3 months. If not, it will take a very longer time, or sometimes it becomes impossible to treat them. So this is where our we first started exploring how we can use additive manufacturing to help or to make a bring down a sort of support in order to treat clubfoot. So in terms of that, going for a deeper understanding, we worked with a couple of orthopedicians in and around Coimbatore with some of the renowned hospitals, and we started exploring how this happens. So as we know that clubfoot treatment starts from the 4th week after a child was born. So they started from the 4th week. So it goes in stages, and each plaster of Paris mold is left on the child for a matter of a week or 10 days, and then they try to slightly regain its position until the child attains a proper alignment in terms of the feet, and that's how the treatment is. So the problem with this particular existing technology is, we all know that the young baby which was born, it would weigh somewhere between 2.75 kilograms to 3.5 kilograms. And when we put a plaster of Paris mold over the child, it would be adding 900 grams of weight on top of the kid's actual weight. So it is like we are speaking of an approximate weight of 30%. We are adding an extra weight to the baby. That is number one. And number two is, when the plaster of Paris cures, it tends to react with the skin underneath, and it causes an irritation which leaves the child with quite uncomfortable. And third thing, when the child has the biological process,